Just to see to demonstrate, what robot sees. The first example is depth estimation. As I said, it's really fundamental. It's a core algorithm that by itself, of course, it's not useful if you don't somehow apply that. Application in our products for this is for obviously object detection. So we combine this depth estimation with the semantic segmentation to understand where the objects are in 3D space, and to be able to detect them and to navigate around them, right? The other application is obviously density construction, when we do the 3D map of the environment. And another one is we also use this in pose estimation of the palettes and other objects that we do. We use information of this dense depth map that we get. Another fundamental algorithm is semantic segmentation. Again, by itself, of course, it was a research topic for the last probably 10 years or more. Here, the application of this is, again, for object detection, to really accurately understand to which class each object on a pixel level belongs to. So that's one application. We also utilize it in pose estimation, and we utilize it in our SLAM. So we use in our 3D SLAM, we use semantic segmentation to filter out dynamic objects, for example, and then also in building the dense 3D map, we use it to really put the objects of interest into the map without putting some, for example, forklifts that you know that are moving, without putting them into the map. So, and the last topic I have for today is really what I like the collaboration between our company Gideon and academia FAIR. There were, multiple collaborations with maybe some smaller initiatives, but one of the biggest one, or the biggest one, was the A-Unit project. So A-Unit stands for Autonomy Unit, right? So the idea was, and on the next slide I'm going to show what kind of the final product was, right? The idea was to develop like a novel hardware PC that has all the necessary computing resources, CPU, GPU, etc., real-time computing resources needed for running autonomous stack of a single robot, right? And also to develop the algorithms, the software that's needed that can run in real time online on this machine. So that was developed for this project. So this project lasted for the last, 3 years or something like that? Yeah. Something like that. And kind of on this picture, this image, we can see the final product, right? Hardware product, right? So this is this computer, this hardware that we developed, right? Just briefly about the specification. So as I said, it has a lot of computational power, including both CPU, GPU in real-time computational power, which is important for communication with drives, communication with sensors, etc. Rough design, water and dust resistant, vibration and temperature resistant. Of course, this is important because the idea is to use that on moving forklifts, moving vehicles, right, that are exposed to different conditions. And a lot of connectivity that's needed to be able to connect, different sets of sensors to it, different sets of controllers, and other components that can have. Another important component is, of course, this needs to run autonomous software. So the complete software needed for a single robot autonomy that includes real-time communication with drives, with sensors, etc. Vision-based perception. I showed some of the components like depth estimation, semantic segmentation, 3D SLAM, for example, AMR style navigation, and then as well some kind of a user-friendly interface and an API towards other systems. So the scope of this project was developing this kind of hardware PC, and then as well developing the algorithms that run on board this PC. So which area did we collaborate with FAIR? So in this project, we collaborated with Professor Petrovic group, right? So that was one group, with Professor Jaco group, and also with Professor Šegić group, right? So with Professor Jaco, we collaborated on embedded software design. So they were involved in developing software for real-time operating systems, right? For also both design and implementation. And they were doing some stuff on embedded safety software design. With Professor Petrovic and Šegić, we worked on these topics that are listed here. Those topics include sensor calibration, multi-sensor odometry, self-supervised learning for depth estimation, anomaly detection, semantic, and AMR style navigation. For example, two particular topics were of interest, which we are not working on, like hierarchical planning and model predictive control that takes into account dynamic obstacles. So Professor showed already a video on how the robot is navigating around people moving around the robot. That's something that we were missing, and that's where we see that where we saw potential for collaboration to kind of increase the capability of our robots. This project finished. It was really quite a successful one. I think all the milestones were delivered. And maybe just as a result of the project, Gideon has filed in the last 3 or 4 years roughly 16 patents related to this project. And out of those 6, I think already 4 or 5 were granted. Others are under examination. So as I said, except for the milestones that were, let's say, assessed successfully, there really brought, let's say, a nice set of patents that we filed. And I know there is a lot of papers that were published by Professor Petrovic, Jaco, and Šegvić. So that's briefly it about Gideon and the collaboration.